Right, today we are going to discuss sequences and series and just kind of an introduction to them. Then the next two lessons, we're gonna discuss specific types of sequences and series. So first we should probably know what a sequence and a series, what they are individually. So a sequence is a function whose domain is a set of consecutive integers. Remember that consecutive means in a row, so like 1, 2, 3, 4, so on and so forth. The terms are the numbers that are part of a sequence. So sequences are usually separated by commas. So you can see here in example 2, these are both sequences. They're separated by commas. The terms are the actual numbers, 2/5, 2/25, -3, 5, so on and so forth. A series is an expression that results when the terms, so the individual numbers of a sequence, are added. So notice that with a series, we have plus signs between. And notice that we use the ellipses here, just like we've used a couple times throughout this school year. There are two different types of sequences and series. There are finite sequences and series and infinite sequences and series. A sequence or series that has a last term, meaning it has an ending place, is finite. A sequence or series that continues without stopping, so goes on forever to either infinity or negative infinity, is going to be an infinite sequence or series. Our last definition is summation notation, which is also called sigma notation because we use the Greek letter sigma for it. And this you've seen twice before throughout the year. When we did the binomial expansion, we used sigma notation, and then we also used it when we were doing the sum of the squared differences in our stats unit. But this is notation for a series, not a sequence, but for a series that uses the uppercase sigma, and it has what's called an index, a lower limit, and an upper limit of summation. And again, summation just means that we're adding them together, and that is part of the definition of a series. But it's only able to be written in summation notation when we have an index, a lower limit, and an upper limit. So if we look further here, I'm going to move this over a bit so I can scroll. There we go. Within our formulas for special series, and you'll see how these come into play in just a moment, I want to take a minute to define index, lower limit, and upper limit of summation. The index is always going to be whatever this is. So my I in this case, that's my index. My lower limit is going to be the starting point here. So that's the lower limit. That's where the series is going to start. The upper limit of summation is always on the top. So you should remember, if you remember the binomial expansion, how we started at whatever the lower limit was and we kept going until we hit the upper limit. So that's going to be true on all of these. Now, these are formulas for special series, meaning if you are summing the series of numbers that starts at 1 and ends at n of 1, that means you're adding 1 plus 1 plus 1 plus 1 plus 1 plus 1 up until you get to n. That's just going to become n because it's n times however many ones you have. If you are starting at I equals 1, where I is a variable, and you are going up to n, that formula, you're always going to be an end result of n times n plus 1 divided by 2. Now, here's something that's important. We need to know how to read these sums. So when we read these, this is going to be read, this thing right here, as the sum, that's what the sigma means, from, then you're going to talk your index and lower limit, from I equals 1 to whatever the upper limit is, n, of whatever it is you're taking the sum of. So in this case, I. So the second one, we would read the sum from I equals 1 to n of I squared. And this is a formula, so whenever you have a variable squared going from 1 to whatever n is, this is the formula that's always going to give you the actual summation, the actual end product. What these formulas do is they prevent us from actually having to write all that work out and find the actual sum. So that'll come in handy here momentarily. So example 1 just says write the first 6 terms of the sequence, and it gives us a formula. This says a sub n equals 5 minus n. So if we are starting from when a equals 1, then that means we've got 5 minus 1, 5 minus 2, 5 minus 3, 5 minus 4, 5 minus 5, and 5 minus 6. So when I do that, that means the first 6 terms of my sequence are 4, 3, 2, 1, 0, and negative 1. So all we're doing is plugging in. So when I do the same thing on B, again, some of you are going to notice a pattern. So you don't necessarily have to write all of this out. If you can do the first 2 and then get the rest, that's great. So on this one, I might do negative 1/3 to the 1 minus 1 and say, okay, 1 minus 1 is 0, anything to the 0 is 1. And then I might not know what's next, so maybe I have to do it again. Negative 1/3 to the 2 minus 1. 2 minus 1 is 1. Negative 1/3 to the first power is negative 1/3. If you know what's going to come next, then go ahead and list them. If you don't, then write out the work. So here, I started out with negative 1/3 to the 0. This became negative 1/3 to the first. So the next one is going to be negative 1/3 to the second power, which I know to be 1/9. Negative 1/3 to the third power is negative 1/27, because all I'm doing is changing the sign. Since the number that I'm taking to a power is negative, I know the signs should alternate, because odd powers are negative, even powers are positive, and I'm multiplying the bottom by 3. So 27 times 3 is 81. I know the next one's going to be positive. Then I've only got one more. 81 times 3 is 243. And I know the next one should be negative. So there are my sequence terms. Example 2 asks us to write the next term in the sequence, then write a rule for the nth term. So these usually go hand in hand, the two parts. So if you can figure out what's happening, you can probably write a rule. So I notice that my numerator here has stayed the same the whole time. So I venture to say that the next term in the sequence is going to have a numerator of 2. If I look at what's happening here, 5, 25, 125, 625, hopefully you notice the pattern that those are all powers of 5. 5 to the first, 5 to the second, 5 to the third, so on and so forth. So this was 5 to the fourth, so the next one should be 5 to the fifth, which gives us the next term in the sequence as 2 over 3,125. Now, when you write a rule for the nth term, that means it needs to say general. So I need to write, this was the first term and my exponent was the first. This was the fifth term and my exponent was the fifth. So my general rule is 2 over 5 to whatever power the term is. So fifth term was fifth, so the nth term would be to the nth. So my rule is 2 over 5 to the n. The next term is 2 over 3,125. All right, next one. Let's take a look at what's happening. -3, 5, -7, 9. There's a bunch of different things that we could try here. But the key that I notice is that I'm rotating signs, which means I know every single time I alternate signs, there has to be something negative raised to a power. Now, this is a case where your rule might not be the same as somebody else's, and they might both still be right. So just because yours doesn't match mine doesn't necessarily mean that it's wrong. Now, the next term in this sequence should always be the same no matter what rule you're using. So I notice I went 3, 5, 7, 9. If I wasn't looking at the negatives, I would say that the next term in the sequence is 11. But because I know I'm alternating signs here, my first one was negative, then positive, then negative, then positive, so this should be negative again. So the next term in the sequence should be -11. Coming up with a rule here is a little bit of guess and check. And there's not necessarily one thing that you can always do to come up with the answer, but you can look at patterns. And what I can look at here is because I know it's alternating signs, I know that my first term was negative. So that means it was raised to an odd power, and first, 1 is odd. So I'm going to put in my rule a -1 to the n because my first, my third, my fifth, my seventh will all be odd powers of a negative, which means they will be negative, while my even powers will be positive. So now I need to come up with a rule to relate n. So here n is 1, here n is 2, here n is 3 because that's the third term, to come up with the rest of it, the 3, 5, 7, 9. So if I just do 1 plus 2, that gets me 3, and this part gave me the negative, but 2 plus 2 isn't 5, so that doesn't work. So maybe you say, okay, well maybe it's 3 times n. Well, 3 times 1 is 3, but 3 times 2 isn't 5. So again, you need to come up with a rule that's always going to work, and it's a little bit guess and check. Here, the rule that I came up with, I did 2 times n, and then I added 1. Again, you can check with me if you come up with something different. It could also be correct, but 2 times n plus 1 is going to give me the 3, the 5, the 7, the 9. This is the fifth term. That's going to give me 11. And again, this part of the rule gets me the alternating sign. So again, you've got to kind of guess and check, but this right here is very important because anytime you have an alternating sign, you should know that you're going to end up with a negative to a power. All right, example 3, write the series with summation notation. So this is kind of like working backward. Again, it's noticing patterns, so it's hard to teach because it's a lot of observing, finding patterns, and then writing it. We know that summation notation, you have to have your sigma, and you have to have a starting point, so I equals something to something else. So let's look at our pattern. Notice that my ellipses are in the middle, and there is an actual ending point. So let's look and see what these numbers have in common. 4, 8, 12, all the way up to 100. Well, the first thing that comes to my mind is that they're multiples of 4. 4 times 1, 4 times 2, 4 times 3. And 100 is also a multiple of 4. It's 4 times 25. So again, maybe you come up with something different than me, but this is where I went first. So because this is the first term, the second term, the third term, this lines up very nicely because this, the 1, the 2, the 3, can be my variable. That can be my I. So 4 times I would describe all of these. 4 times 1, 4 times 2, 4 times 3. So I'm going to do 4 times I. I'm starting at when I is 1, because I started with 4 times 1, and I am ending when I is 25. So from I equals 1 to 25 of 4I. And again, this is a case where there could be multiple correct answers. So if you come up with something different and want to check it, I'd be happy to check that for you. All right, let's look at the next one. The first thing I want to do when I see this is I see a term that doesn't belong, a format that doesn't match. This 2 doesn't look like the others. So I'm going to give it a denominator and see if that helps me. So I'm looking for patterns. And again, I've gotten good at these because I've spent a lot of time looking at these. As you do more, you will get better. So when I look here, I look at my numerators and I see that they're increasing by 1. So 2, 3, 4, 5, ... seems to go on forever. So if I say that I'm going to start when I equals 1, and you don't always have to start at when I is 1. You can start when I is 0 or I is 2, whatever works for you. But if I is 1, this numerator increases by 1 every time, and the first numerator is 2. So I'm going to describe this as I plus 1, because when I is 1, I get 2, when I is 2, I get 3, so on and so forth. The denominators, when I is 1, 1 is 1 times 1. When I is 2, I get 4. When I is 3, I get 9. When I is 4, I get 16. What am I doing to the 1, the 2, the 3, the 4 to get these denominators? Hopefully you recognize those as squares. So this is I squared. Now, there was no last term, which means this is an infinite series, which means that our upper limit gets a pretty infinity sign. And look at how fancy and grown-up math that looks. So there is our series. Example 4 asks us to actually find the sum of the series. So this is where we are going to be using these formulas. Now you could, because this is a small series, if you wanted, you could actually plug in the numbers and work all of this out. So I'm going to show you how you could do that. You could start at when I is 1 and do 2 times 1 squared minus 1. And then add that to 2 times 2 squared minus 1 plus 2 times 3 squared minus 1. And remember, we stop at the upper limit, so 2 times 4 squared minus 1 and 2 times 5 squared, of course I'm running out of room, minus 1. And you could actually work out the math for each of these and add them all together. That will give you your sum. Now I'm going to tell you that that won't always work, because if this number is 100, there's absolutely no way that you have time to do that. So I want to show you an alternate way. Again, I want you to know that you can do this for small sums, because if you forget how to use these, that can always help. But what you should be doing here is separating this, because this 2i squared minus 1 means that what you can do is this is 2 times I squared. So since this is an I squared, I can do 2 times the I squared formula, so n times n plus 1 times 2n plus 1 over 6. So 2 times I squared minus the formula for 1, which is just n. So that means that all I have to do is plug those in. So I equals 1 to n. So I plug the upper limit, because that is the n, again, notice that up on all of these, n is the upper limit. So when I'm plugging these formulas in, which by the way, you do not have to memorize, these will be given to you on the quiz. So I plug in my upper limit, 2 times, and then I've got my upper limit is 5, 5 times 5 plus 1, which is 6, 2 times 5 is 10, plus 1 is 11, over 6, minus 5. So, order of operations in here, notice that the 6's are going to cancel each other out. So I've got 2 times 55 minus 5. So 2 times 55 is 110, minus 5 is 105, which is your answer. Again, on a small limit, you could actually plug in, show your work, and get the same answer. But when this goes up to like 100, you need to know how to separate and use these formulas. Again, you do not have to memorize these formulas. They will be given to you. All right, last one. 1 year before a trip, you begin making deposits into an account. The first month, you deposit $40. For the next 11 months, you deposit $3 more than the previous month. Write a rule for the amount of each monthly deposit. When we write a rule, we write it like what we see in example 1, a sub n. So saying when you are plugging in whatever n is, so in this case, we probably want n to be the number of months. So write a rule. Again, your rule might be something different than mine. It says the first month you deposit $40. For the next 11 months, you deposit 3 more than the previous month. So my first month, I deposited $40. Then the next month, I'm going to deposit $43, then $46, so on and so forth. Now, sometimes, and again, it all depends on how your brain works. For some people, it is actually easier to answer B first by actually doing this and then write the rule. Some people who think more abstractly prefer to write the rule and then use their rule to come up with the answer. So I do not care which way you do this because I'm not going to force your brain to work one way or over the other when you have both to do. So if you want to answer this one first, go right ahead. 40 plus 43, you can add them all up. 46, 49, 52, 55, 58, 61, 64, 67, 70, and 73. If you want to add those all up, go for it. You should get $678. Now, to write a rule from this, again, you may have to do some guess and check. Whatever month it is, you want it to, the next one, to be 3 more than that month amount. So that means in the second month that I deposit more, other than my initial deposit, this month I added 6. Here I added 9 from the original. So from the 40, I added 3, I added 6, I added 9, so on and so forth. So the way I wrote this is I wrote this from I equals 1 to 12. But you might write it from 0. And if that's the case, that's fine with me. So you can write your rule like this. I did $37 as the kind of just the floating amount. And then I wrote 3n, where n is the month number. And this is just the amount of each monthly deposit. So 3 times 1 is $3. Add that to the 37. My first month, I deposited that amount. Then 3 times 2 is 6. 6 plus 37 gives me the 43. So I wrote this, which then led me to a summation from I equals 1 to n, or 12, I mean, I equals 1 to 12, of 3n plus 37. So again, if I'm using my shortcut here, n here is going to be n times n minus 1, so 12 or plus 1 times 13 over 2 times 3, and then plus the 37. So again, multiple ways to come up with this answer. If you prefer just to add them, go right ahead. If you prefer to use this to write a summation and then do one step to get the answer, you certainly can do that as well, because here it does not specify how you have to find the answer as long as you find it. So I think that this section really shows how sophisticated we have become with our math learning, because this looks awful fancy. So I think that this proves that math is great.